Hi, I'm Sam, and in this video we're going to be looking at string matching using finite automata. There are many algorithms for string matching, but here we have to look at using finite automata. Before I explain how this works, it's important to discuss in what cases the finite automaton matcher algorithm, or FAM for short, is used. FAM is not the most efficient or simplest algorithm for string matching. However, its importance lies in being able to recognize regular expressions. Because of time constraints, I'm going to assume that you know what regular expressions are and how they work. In the rest of the slides, I've represented A+ and A* with brackets around them to make them clearer to see. So for this string, these parentheses wouldn't be part of the actual string. So where is the FAM algorithm used? Well, most importantly in compilers, more specifically during parsing. For example, the syntactic tokens that make up the coding language are defined as regular expressions. So how does string matching using finite automata work? Well, the finite automaton used is a quintuple given by q, epsilon, delta, s, and f. Q is a finite set of states. Epsilon is the set of all characters within the regular expression and the input string we are considering, or the finite input alphabet. Delta is a transition function that defines the transitions between states depending on the input. S is a state within Q that is the start state. F is a subset of states within Q that is the set of accepting states. So say we needed our FAM algorithm to identify whether a string ends with the string AB, AB, C plus D. The easiest way to see how it would do this is to look at a state diagram. So in this diagram, the set of states Q is represented by the green circles. The start state is state 0, and the accept state is the final state AB, AB, C plus D. The transition function is represented by the arrows. If there is no arrow for a particular input character, this means that on this input go to state 0. So in our current example, our input string is going to be as given here. We start off at state 0. Our first input character is A, so we follow the arrow labelled by A. This takes us to state A. The next input is B, so we follow the transition B to state AB. Notice up until this point the input string is underlined. This is to represent what the algorithm thinks might be the final string it's looking for, AB, AB, C plus D. However, the next input character is A. AB, AB, A is not part of the string we are trying to identify. The state diagram takes us back to state AB, A. This is because while the whole string seen so far doesn't fit, the last two characters with the next input A on the end does. I've represented this again by underlining these characters. The next input is D. ABAD doesn't fit the string we're looking for, and no part of ABAD does either, so we go right back to state 0. So now we just do as we did before. We can see here how our state machine handles the repeated character C+. Every time a C is entered, it simply takes it back to the same state. So after the final input D, we end up in our accept state. This means that the input string is accepted. All the transitions in our state diagram can be represented here by this transition table. This is essentially how our algorithm holds the information of the transition function. So to actually employ the FAM algorithm, we use this finite-state matcher function here. B is our input string, and delta is the transition table. This function is very simple. Lines 4 to 6 simply step through the states as we did before in our example, using the transition table and Q to hold which state it is currently in. So if the value of Q is equivalent to one of the accept states that are defined by the transition table, then string B is accepted. But how do we actually create this transition table? We use this compute transition function. A is the string or regular expression we're looking for, and epsilon is the finite alphabet. The loop at line 3 is going to run through once for each character in the regular expression A we are looking at. Q is going to represent the state which we are currently looking at. The for loop at line 4 goes through each character in the finite alphabet we are using. Line 5 sets variable k to the smaller of m plus 1 or q plus 2. It will become clear later that we want k to start off as the smaller of m or q plus 1. However, k is immediately decremented by 1 in line 6, so we use m plus 1 and q plus 2. So what k represents is the string represented by a state. So in the previous example, if k was 6, it represents AB, ABC plus D. If it was 5, AB, ABC plus, etc. Another way of looking at this is that k represents the first k characters of A, the regular expression we are using. The easiest way to look at line 7 is to see it as until ak is the suffix of aqx. So what on earth does this actually mean? Well, the easiest way to describe it is to give you another example. Here is part of the transition table from the example we were looking at earlier in our finite state diagram. The numbers in brackets are what k would be in order to represent this state. So for example, if k was 3, it would be state ABA. So for our example, we're going to assume that the loop at 3 has taken us to state Q, and the loop at 4 has taken us to character A in our input language. Looking at line 5, this would give us a k of 6. Line 6 is immediately run, giving us k equals 5. AQX is given by the string represented by state Q, with the character of the input language X we are currently looking at concatenated on the end. So looking at our segment of the transition table, in this case AQX would be given by ABABA, and AK would be ABABC+. So we can see here that AK is not the suffix of AQX. That is, the last k characters of AQX are not AK. So the loop continues, but AK is still not equal to the suffix of AQX. The loop runs once more, and this time AK is the suffix of AQX. The repeat loop is exited and state k is assigned to delta QX. Due to the for loops at line 3 and 4, this process is repeated for each state and each character in the language, so a complete transition table is produced. So what is the running time of our FAM algorithm? We'll start by looking at the finite state machine matcher. It's easy to see that lines 4 to 6 will be run size of b or n times. So this part of our algorithm has order n. Now we need to look at our compute transition function. If we assume we are using a very poor string matching algorithm to check if AK is the suffix of AQX that needs to compare all characters in AK to the last k characters of AQX, this line has an order of k. In the worst case, line 5 sets k to m plus 1, and the loop repeats until k equals 0. So knowing line 7 needs k comparisons each time the loop is run, and k is originally equal to m plus 1, we can say that lines 5 to 7 have an order of m plus 1 factorial. This loop runs through size of epsilon times. The outer loop runs length of a or n times. Putting these all together, we can say this function has a runtime of m factorial times m times size of epsilon. So the total running time for our FAM algorithm can be given by big O of m factorial times m times the size of epsilon plus n. However, this could be improved upon. If the string matching algorithm we used for finding if AK is the suffix of AQX, the runtime could be reduced to big O of m cubed times epsilon plus n. In fact, there are algorithms for computing the transition table that are much more efficient than what I've shown here, and we can reduce the entire runtime to m times the size of epsilon plus n. So that's it. Hope this helped you. Thanks for watching.